Casper, could you check whether you can allow people in when someone joins the meeting room? No, the waiting room, because otherwise I'll be a little bit disturbed each time someone joins. So welcome everyone, and it's been some time now since the last time. We sort of hoped that this thing would blow over sooner and we could actually meet up. So that's one of the reasons why we haven't done anything. So we got this email from the Go Developer Network, which is we are part of on Meetup.com, and they said that Bill would like to do or volunteer to do like some talks about the new generics draft proposal. And that's sort of what we'll be doing today. Since the last time, yeah, this is a little bit about our group. So we're sort of a new group. This is our third meetup. So we're sort of also trying to find out what the group's interested in, and like if there's something that you would want like from this group, or something that you want to hear about, or if there's something that you would like to present, please reach out to us. Like that would be a great help. So since the last time we got a new guy on the organizer team, Frederik Mogensen. I don't know if he's on. Yes, he's on the call.
Hey guys.
So we got very, very impressed by his awesome presentation last time. So no, he's a great guy, and it's nice to have a new face on the organizer team. I think that's it for the introductions. Now we'll have a talk, and I'll hand the word to Bill.
Brilliant. Thank you for coming out. I know it's late where you are there in, you said Denmark, right? It's 8 p.m. So I'm going to need about an hour to give the talk, and then we have as much time as we want after that to discuss. There's about 20 plus people here, but it's still fairly small, and I think everybody can have an opportunity to provide a comment or question. So let me just give you the ground rules. Because it's going to take about an hour to get through the material, I'm not going to stop and take questions during the talk. All right, so I'll take all of the questions at the very end when I'm done. That being said, I want the talk to be interactive between everybody that's here. So please use the Zoom chat window here and talk about everything that I'm showing you. If you want to ask questions in there for other people to answer, go for it. I won't be able to look or really read the chat while we're going. So I'm going to kind of stay blind to that. But definitely interact with each other and talk and discuss everything that's going on. And then at the end, I'll give everybody 2 or 3 minutes to ask questions and or make some comments. The goal of this talk is to present to everybody the current draft proposal syntax. That's all the draft is right now. It's a syntax proposal for what generics could look like in Go. It's actually pretty stable now in terms of where the syntax is. The language team is happy. The discussions have kind of died down, and they're actually starting the very beginnings of looking at a compiler implementation of this. We currently don't have a compiler implementation. We just have a tool called Go2Go, which is a transpiler. So don't think you're going to start using this in production just yet, okay? All right, we don't really have a compiler implementation yet. Right now, the language team is thinking that if life is really good between now and August of next year, the 1.17 release, we might actually have a compiler implementation of this that we could start working with. I think it's going to be in 1.18, February of 22, but maybe I'm just being a pessimist. So we'll see. So we're looking at August next year or February of 22, and then we'll have something I think that's going to be really interesting. just to give you some timelines. And they're just starting now to look at the compiler implementations, which is cool. Okay, because time is always against us, Eric, switch over to my laptop here. Let me get into my speaker view so I can see here. I have a monitor in front of me that I can see what you can see. Zoom never gives us very good high quality video, so things will be a little larger in font to compensate for that. Eric, drop those 3 links into the chat window too. Eric is someone that works with me, and he does a lot of the production stuff that we're doing here. I'm in my studio today. So Eric is dropping 3 links into the chat for everybody. The first one is a link to the repo, which I'm showing you now. This is where the material is for the talk. The next link is the draft document. If you want to read that at some time, you can get to it here from the repo as well. I'll show you. The third link is a Google survey that gives you an opportunity to anonymously talk to the Go team that's working on this, and they'd love to get your feedback. So that's your opportunity to kind of give you feedback to help shape what's happening here. Now I'm showing you the Go training repo. This is where I've been collecting and building examples. We are not in 1 hour going to have time to go through all 13 of these. We're only going to get through the first 5. But if I get through, or when I get through the first 5, you will have seen at least 85%, if not more, of the draft document. Most definitely what's important here in terms of the new syntax. I also want to explain in this talk not just what the new syntax is, but why we need a new syntax, because I think it helps to understand why. And then it's just, when you understand why, everything else just kind of seems to start to fall into place. So I'm going to talk about both the why and the what, but we'll go through those 5. So the other examples, 6 through 13, will be available to you to look at after the talk, or if you want to explore and experiment with the generic syntax after the talk. Now, the README has a few things here I want to quickly show you. There's a link that says here, and that link also opens up to the draft document right there. You can see it was updated about 9 days ago. And I think where we're at and what I'm going to show you right now is pretty stable and isn't going to change as relates to what we will see for a first release in that August 21, February 22. There's also a playground, a Go playground that will allow you to experiment and test out the syntax. This runs the Go transpiler. I won't be using this in this talk, but if you have code that you want to share with me during the Q&A period, create some links and then you can drop that in the chat and we can look at them as a group. And this lets you kind of experiment with the syntax and explore what's there. Also, this is the high-level overview that I've taken from the draft. This is what the first release, remember, when we talk about August 21 or February 22, 17, 1.17 or 18, we're talking about just the very first release of generics in Go. And currently, this is what is being focused on for that first release. This is essentially what I'm going to be showing you over the next hour. I'm not going to read it. You've already read it. You'll get a general sense of what we're going to be talking about. This is also at a high level, the admissions, or what is currently not being slated for the first release. This doesn't mean that this might not make a second or third release a year or two in after the first release. All right, so the meta programming, the specialization, things that you'll see in other programming languages today. It's just not being worked on right now because the syntax just has to be right, because once this gets released, there's no going back. And so really this first release is really about the syntax and where we need new syntax, and if this still looks and feels like Go. And these are the things I want you to be thinking about as I go through the code. Oh, I've got to update this. I just published a new post yesterday. So I've got a part 3 now on this post. And these are just some posts that people put out, including myself, that I think are pretty good if you want to read more. And then I've got the Go tooling installed locally. These are the instructions to do that. It's what I've done. And basically that means that if I type go version, or make this a little larger, you can see that I'm not running 1.15.2, but a version from source that was updated about 6 days ago. All right, 6 days ago. Okay. And then we're going to go through all of the, again, the first 5 examples. Okay. So right now it is a quarter after the hour. So pretty much at about this time in the next hour, I should be done or really close. I'll keep my eye on that clock. And I'm going to switch over to VS Code to do this. I'm going to try to stay at this font level if I can. I see what you can see, so if I just can't, I will go bigger. Maybe I'll just go bigger anyway. I'm going to go bigger anyway. It'll just help. Okay, so let's start with this first example of generic functions. Now, one of the things I want to do here is not just show you the new syntax, but also explain why we need a new syntax in the places that we do. And I want to do this through a progression of writing code that we can today in 1.15 and go through what we obviously can't. Or the other thing I really want to focus on as we go through this code is generics isn't being introduced into the language as a way to write more performant code. So let's get that out of our head. This is not about, well, will generics give us code that's faster than, let's say, our current runtime polymorphism? The answer is 1, I have no idea because we haven't implemented this compiler yet. And 2, that's not our priority. Our priority needs to be, and I will focus on this in the talk, is the code more readable? Can this code be understood? Is it more comprehensible by more developers? And then we want to add to that trade-off of readability and comprehension the maintenance side, because there's a code maintenance cost and benefit to all of this as well. And that's really what we're going to focus on in the next hour. So let's start here. Let's start on line 13. I wrote a function called print numbers. And the idea of this function is that it can perform a linear traversal over a slice of integers, displaying, outputting each individual integer in the collection. As you can see, print numbers, it takes a slice of int, that's our collection of integers, and then it has a header on line 14, an extra character line return on 18, and then between 15 and 17, we use our basic language syntax and mechanics to perform a for range across that collection of integers, and then using func to print each one. So essentially, I've got 5 lines of code here to perform this operation. And I'm going to make a big, bold statement right now, and I'm going to say that I believe that every Go developer, even those brand new to the language, even those only a couple of days in, can read and comprehend these 5 lines of code. This is one of the things we love about Go. I can almost make an argument that even if you've never seen Go before, but you're a programmer with a year or 2 in, that you can read and comprehend this code. We love this about Go. And the big reason we can all read and comprehend this is because we're using our language syntax and our language mechanics to write this. Now, here's the thing. If I want to perform the same sort of printing operation, but this time I want to operate against a collection of strings, well, essentially it's going to be the same 5 lines of code, with the only difference being maybe the variable names to stay in context with the fact that we're dealing with strings, and I've changed the header out. But outside of variable names and the header, this code is essentially the same. It's the same 5 lines of code, which is great. Because if we got high levels of readability and comprehension on the first function, well, we're going to have it again on the second function. The only thing is if I want to now do this with a collection of floats or a collection of users, right? You get where I'm going. Now I need a third function, I need a fourth function, I need a fifth function. And so though I can constantly make the argument that each of those functions, those 3, those 4, those 5 functions, have high levels of readability and comprehension for our team, maintenance is now starting to become the trade-off, because now there's 5 functions, right? We have basically 25 lines of code that we have to maintain. And the more lines of code you have, well, the more opportunity for bugs, the more maintenance. We can have those conversations all day. And so even though our readability is high, our maintenance starts to drop off. So I start thinking about this problem with Go today, and I ask myself, well, is there a way to maintain the same high level of readability, but somehow reduce the maintenance cost by maybe consolidating all of this code into a single function? Maybe that's the win here. Maybe that's what we need to do. And when I think about that, I get to this function here, which I've called print assert. And the idea is to take all of those functions that I was going to have to write, at least the two I have now, and try to consolidate all of that into a single function. Now, we could see here that we're talking about 11 lines of code, but again, as we add more collections here, the amount of new code is going to be diminished. But we've got a couple of wins here, and I think a couple of losses. The first thing here is, if we want this function to be able to work with that slice of int and that slice of string, then we've got to be able to pass a slice of int and slice of string in. And the only way to be able to do that is to start to write code that uses our traditional polymorphic mechanics, and that's basically interfaces. Right? Our concrete functions are functions that ask for data based on what that data is, that slice of int, that slice of string. That's where we were before. But our polymorphic functions, they ask for data based on what that data can do. And that's how we're able to write a function that can accept multiple concrete pieces of data, not based on what they are, but based on what they can do. Now, in this case, we don't particularly care what the data can do, and that's why you see here the use of the empty interface. It's still a polymorphic function because it's able to accept data of any type, because essentially we don't care at all about any given behavior, which is why we're incredibly blind at all levels on what that data is. But it's a polymorphic function nonetheless. And so now on line 37, what we need to do is begin to inspect what the concrete data is inside that interface value V. And there's two mechanics for this in the current language. What you're seeing here is called type assertions. In fact, I'm performing a generic type assertion right there on line 37, which can be done on a switch with the keyword type in the brackets here. And basically what we're saying is, since we're blind to the concrete data stored inside of V, our generic type switch here, generic type assertion says, well, if there's a slice of int inside of V, then execute this code. If there's a slice of string, execute this code. And essentially, this is the same language, syntax, and mechanics we were using before with the different variable names for context. And so we do have that readability that we wanted, and we do have the consolidation to help with the maintenance. Now, we do have one change in semantics. It's quite possible that somebody passes in just a user or just an int or just a string. There's no way at compile time to prevent anything being passed in here that we don't want, because we're using the empty interface, which means that we could pass in even a slice of float right now and we won't see any output. So a little bit of a change of semantics, but look, I'm able to consolidate. But let's be honest here. This isn't really a generic version of print, because if I do want to work with a slice of floats, I have to write more code. So I think we're getting better where we're maintaining our readability, and we've consolidated the amount of code we need to do this. But the next question that pops in my head is, well, it would be nice to just write this in a generic way right now. Is that even possible in Go today? And the answer actually is, yeah, I could write a generic version of this print function if I use the reflect package. Now, this function, again, has to be a polymorphic function because we have to be able to accept any piece of concrete data. But since we don't care what it can do, we use the empty interface And now, again, we're blind. But instead of using type assertions, we switch away from our language syntax and mechanics, and we go to an API solution, which is using the reflect package from the standard library. And now we went from those 5 lines of code we started with to 8 lines of code, only 3 more. But if you stare at this code, it's not really obvious what it's doing and how it works. It's not obvious like those first concrete versions of print that we wrote. And that's really because we've walked away from language syntax and mechanics here, and now we're API based. And so not every Go developer can basically read this code and understand and comprehend what's happening immediately. So we've lost some readability here. But whoa, I think we've gained some high levels of maintenance because it's only 8 lines of code that we have to maintain. But if we break through this code here, all reflection starts with that value of call that you see on line 58, and it gives us the ability to get a reflect value that we can use to inspect at runtime the concrete data stored inside of V. We can ask questions like, well, did the caller even give us a slice? If they didn't, there won't be any output. Now, we can't use our 4 range mechanics. Again, we've walked away from our language syntax here, but we can iterate a variable I across length using, again, the API of the reflect package. And then we can perform our linear traversal by using the index method over I, and then interface gets us to that concrete data, and then we have print to display it. So this is a generic version of print. I can pass a slice of float, a slice of user, the int, the string, and we'll get output. Again, we're not getting any compile time checks, so a caller could pass in data that we can't iterate over. We won't blow up, we won't have any output. And it's all API based, but it still is a generic function. In fact, all of the code that I've shown you so far is kind of leveraging generics in the sense that we're all using func.print. I mean, func.print uses the reflect package underneath as well to be able to display a value of any type using defaults. So if you see here, I mean, we're already kind of leveraging this form of reflection-based generics in Go anyway. But here it is, 8 lines of code. So what did we gain with this function? Well, we gained maybe higher levels of maintainability because it's the only 8 lines of code we have to have maintained, but we lost readability. This code isn't as comprehensible as the other code. And so I get back to this idea of, is there value in having the ability in the language to write a function like this, like print, where we can have the same high levels of readability we started with because we were using language syntax and mechanics, and then also gain that high level of maintainability because we only have to maintain those same 5 lines of code and nothing more. And I think the answer is yes, at least for me. I want code where the average developer on my team can comprehend it and maintain it. That's what's going to give us the ability to sustain software now, a year from now, 5 years from now, 10 years from now. And this is one of the problems that the current release of the draft syntax is trying to solve. This need where currently we write these polymorphic functions using the empty interface, where we either have to use type assertions or reflection to get to the readability or maintainability wins here. And so I want to show you what this print function could look like with the new draft syntax. And before we explore it, I want you to notice that the 5 lines of code that I've written for this function are really identical to the 5 lines of code that we started with. I want you to notice that we're back to using our language syntax and mechanics, the same 5 lines of code I said that gave us the highest level of readability and code comprehension in the language. This is beautiful. This is what generics can give us, the ability to write concrete functions that are not tied to one concrete piece of data. Concrete functions that can ask for data based on what it is, but at compile time we can figure out what is. That's where we're trying to go. Now, I want you to understand why we need new syntax to even be able to write code like this. And to do that, I'm going to take out the new syntax for a second, and we're going to come back to it. If you just look at this function on line 81, just look at it. You know what I'm trying to do, right? I mean, you see that I'm trying to say, I want to write a function named print that accepts a slice of t, but not really t, right? Some type t to be determined later. You all can see this and understand what I really want to say to the compiler, that I don't want this type t. Really, I want to substitute t for something later at compile time. The problem is right now that this syntax, what we have in front of us, and our need to maintain backwards compatibility with the language, means from the compiler's point of view that somebody somewhere, right? That somebody somewhere is going to be doing this at some point in the code before you hit the build button, right? Before you say go build, the compiler assumes in this syntax that t is going to be declared somewhere where it can find it to satisfy what this function is declaring, which is a slice of t. And the reality is this is the exact opposite of what we want. We don't really expect that there be a type t declared before I try to build. And so this is why we need the new syntax, because if we're going to maintain backwards compatibility, we've got to have a way to tell the compiler that t is not some named concrete type that's going to be declared, but that t represents a generic type that needs to be determined later. Now, what the current draft says is, if you want to declare a generic type to be determined later, well, then what we're going to use is a set of square brackets, in this case, in front of the function name, and then you can name that generic type anything you want. There's no restriction. I mean, I could call it Tom. I can call it lowercase Tom. These naming conventions we're going to have to develop over the next year to have some good standards and idioms in the community. But what you're going to see me do with things like slices is just use a single letter, capitalize, because I think for me right now, this is not something that we normally do in the language with identifiers, at least type identifiers like this. And so it does kind of stick out. And so this set of square brackets in front of the function name before the parameter list is a way of declaring the generic type identifiers for this function. But the draft says one more thing, and that's that every type identifier that you declare must have a corresponding constraint associated with it. Now, the last two examples in this talk, I'm going to focus heavily on constraint. The idea of constraint is whether t can be anything or it's restricted to a domain of, let's say, other concrete types. When there is no restriction on what, in this case, t can become or be substituted for, we're going to use the pre-declared identifier any. Any is essentially an alias to the empty interface, and it represents the fact that there really is no constraint against what t can be substituted for later. But we must have a constraint. And just so I won't have any examples in this talk, but you can have as many of these generic type identifiers as you want, as you need. This is one way to say t, j, and k to be substituted later can be anything. But if there's going to be unique constraints, you can give each of them their own constraint in front of the comma as well. It all depends on what you're doing. For the examples I'm going to be giving you, we're going to be using single generic type identifiers, and at least for now, I'm not going to restrict or constrain anything related to what t can become. And so now you understand why we need the new syntax, because we've got to be able to tell the compiler that T is just, it's not a struct type. It's not some concrete type that's going to be declared by some developer before we try to build this, that it represents a generic type to be determined later, but a concrete type. And because T represents a concrete type, like an int, like a string, like a user, we can then write code using our language syntax and mechanics as if T actually is that int, that string, that user. And that's where we're going to get that high level of readability. And that's where we're going to get the high level of maintainability. Because this generic function is essentially a concrete function asking for data based on what it is. It's just that we get to determine what T is at compile time. That's the big win. It's polymorphism, but not our traditional polymorphism we have today that's at runtime. This is compile time polymorphism. We determine what T is at compile time. Okay, brilliant. I'm going to show you this running. So we need to run the transpiler. And so what I've done in main is on line 92, I've constructed a collection of integers using our sliced construction there, our literal construction on line 98. I'm constructing a slice of strings. There they are, and I can pass that slice of int into those 4 functions, pass that slice of string into the other 4 functions. And if we were to transpile, build, and run this code, let's get into O1 here. We should see the same output. Now, because of the version of Go I'm using, there is a tool called Go. There it is. That's the transpiler. And then I can say build or run and give it the .go2 file, which it's expecting to have. So this .go2 file will get transpiled into a Go file. Then that will be run, and we get output. There it is. And we see it's the same output for the same collection. Now, what are we really trying to accomplish here? The idea, again, is I don't want to have to write more code to work with another type of collection. Gives me that same high level of readability because we're using language syntax and mechanics, and we get the high level of maintainability because it's just 5 lines of code regardless. And to show that, all we need to do is construct maybe a collection of floats using our float 64, making these just decimals. And then we could use our 2 generic functions. Remember, print reflect is a generic function using the reflect package. This is a generic function using our new generics syntax. If I did all of that correctly, we run it again, we're now able to print out those floating point numbers. And so, one of the big wins here is, again, I'm back to just 5 lines of code. Now, there's one more thing here that if we didn't have, maybe this isn't as elegant as it otherwise could be. Now, a big part of the compiler implementation is the idea of being able to infer at compile time what T is going to be. Remember, I keep saying that what this represents is a slice of some type T to be determined later. Now, what we really want to be able to say in as many cases as possible, that later is determined by the compiler at compile time. And that's exactly what's happening right now. If you notice here, I'm just passing in numbers and floats, and the compiler is able to identify, in this case, that T must be an int or T must be a float. And the reason it's able to infer that at compile time is because we're using the generic type identifier as one of the input parameters. So the compiler can see that what we're actually passing is a slice of int, and so T must be an int. Or it sees we're passing in a slice of float. T must be a float. And it's nice that we get the inference, because then making the call is no different than making any other function call we do today. But what if T wasn't being used as an input, right? Let's say we weren't using it as data input. Maybe T is just being used as part of the implementation. Now there's nothing that the compiler can leverage to infer the type at compile time. So does that mean we're lost? No. One of the nice things is, just like these parentheses act as a way to pass data into the function, these brackets also represent a mechanic of being able to pass type information for T. And we'll do that in cases where the compiler isn't going to be able to infer the type. In other words, I can pass the type information in as part of the call and tell the compiler, in this case, don't worry about being able to infer the type at compile time. I'm going to explicitly, at the call site, tell you what T is going to be. It's going to be an int. It's going to be a float. And you'll see that this code runs exactly the same. Now, I would prefer the syntax where the compiler is inferring the type at compile time, again, because from a usability perspective, from a readability perspective, our brains are kind of already wired that way. But we do have the ability to explicitly pass the type information in for those generic type identifiers in those cases where the compiler cannot infer the type at compile time. So this is why you'll hear me say that we're going to accept a slice of some type T to be determined later, because that later may be at compile time if the compiler can infer it. It may be at the call site where we explicitly tell the compiler what T is going to be. But here we are writing basically concrete functions where we can substitute the type information at compile time. And we get our polymorphism, and we get these functions that allow us to work with our language syntax and mechanics. Again, giving us this high level of readability, higher level of comprehension, and maintainability. Okay, brilliant. So we've now seen this generic function. I've shown you the base syntax. I've explained why, but there's more to go. The reality is that if we're writing real-world programs are driven against real-world data. I always say that Go is a data-oriented programming language, that any problem you've ever solved in code is a data problem. It's a data transformation problem. Think about it. Every function you write is a data transformation. There's some input, you transform it, there's some output. There isn't a single program that you've ever written that isn't driven by data. And so generics are going to find themselves in the data types that we're going to be declaring. There are going to be opportunities where at compile time, we may want to determine what that concrete type actually is. Again, to give us the ability to write concrete type of language syntax and mechanic code with that maintainability. Now, there's two types of user-defined types in the language that you can write. There are user-defined types that are based on underlying types, and then there are those that are based on a struct type. We're going to start with the underlying types. Okay, and we're going to go through a similar exercise here, just so we can see the progression of how we can do things, and then how the generics give us that higher level of readability and code comprehension. So on line 15, I'm defining a vector, a name vector int, which has an underlying type of a slice of int, which means this vector can work with collections of integers. On line 24, I've done the same thing, but we're going to work with that slice of string. And once again, if I wanted to work with floats or users or anything else, I've got to define the new type. We get that, you see that, high levels of readability, lower levels of maintainability. But just to make this example a little more interesting, I've added a method to the vector named last. Now, this last method does a couple of interesting things. It returns the value in the highest index position in the vector. It returns a value of the same type that the vector is managing. So on line 17, this last method returns an int. On line 26, this last method returns a string. Now, if you look at the implementation, the 4 lines of code that we're using to write last, once again, they are identical minus really just one thing. Look, we're going to check to see if the vector is empty, because if it's empty, what are we going to do? We're going to return an error. But not only are we going to return an error, we're going to follow the other Go idiom and guideline, which says that if you're returning an error from a function, then return the 0 value for all those other arguments. And we like to do 0 value literals or construction on the return site to gain higher levels of readability. And so on line 19, we're returning the literal value of 0, which is a 0 value for an int. But on line 28, we're returning the empty string, which is the 0 value for a string. There it is. And then if it's not empty, we return the 0 value for the error interface, which is nil, and then the value in the highest index position. Again, all this code is the same. That being said, could we do something a little bit more generic in the current language that we have today? And if we look at this, I could go back and create a vector that would be polymorphic using the empty interface. Remember, this gives us the ability to store any type of data we want as long as it exhibits the full method set of behavior defined by the empty interface, which is nothing. Now, this vector actually changes some of the semantics, and I think this vector creates usability issues because our other vectors that I defined before, my concrete vectors, worked with just one type and one type only. We knew when we called last what we were getting back. But this vector, trying to be generic, kind of starts to break down because I could store different types of data at the exact same time inside this vector. I can store a mix of integers and strings and floats and users, which means that when I call last and I get back the empty interface, I have no clue what type of concrete data is actually stored in there unless I can do more inspection. There's usability issues here. Now, it's the same 4 lines of code where we're returning the 0 value for an interface here, just like we do here. So the implementation isn't adding any extra readability issues, but the usability for sure. Now, what could this look like using generics? This is what we're going to have here. And once again, as I will do throughout the entire talk, I will remove parts of the new syntax so we can explore it and bring it in earlier. Now, you know, once again, what I'm trying to do here. I'm trying to tell the compiler that I want to define a type named vector whose underlying type is a slice of some type t to be determined later. As soon as I say some type t to be determined later, we know that t now needs to be defined as a generic type. And at least right now, the constraint is that there isn't any. T can be anything. That now allows the compiler to know that T represents a generic type identifier to be determined later, either at compile time, if it's possible, or if it's not, it has to be provided explicitly at the construction site of a vector. Now, what gets super interesting here actually is the last method. I want you to notice the receiver. This is a value receiver, right? I get rid of the new syntax. You can see it. This is a value receiver. This method is going to operate on its own copy of a vector. But a vector in and of itself doesn't mean anything if we don't know what concrete type is being used for the underlying slice. And so when we have a type declared with a generic type identifier, that type needs to have represented what the underlying type is going to be. We don't know what the underlying type is yet. This is a method bound to that type on line 56. So what we're going to say is that this is a vector of whatever type t we use to construct this vector. So whatever type is identified at construction flows through the receiver. And so you're going to see those square brackets with these user-defined types, because a vector is only as good as what type T it is. Now, what gets more interesting to me is the return, because on line 58 here, this function has to return a value of that type T. Now, if we look at this real quick, we really have the same 4 lines of code. We check to see if the vector is empty. If it is, we return an error. If not, we return the value at the largest index position, which will already be of type T, no problem, and or nil. But it's this right here that causes a little pain, right? Because we have to be able to construct a value of type T set to its 0 value. But it's more important than that. We've got to have a way of doing that universally. What do I mean? Your first instinct might be, Bill, why can't we just do that? Why can't I do empty literal construction of type T for the 0 value? Think about what that syntax is. Empty literal construction. I didn't say 0 value construction, empty literal construction. Now, if T ends up being substituted for a struct type named user, that syntax is legal. When it comes to struct types, empty literal construction does represent 0 value construction. However, what if T gets substituted for an int? Is that legal syntax? No, not. You can't do that. The concept of literal construction, especially empty literal construction against an int, it doesn't even make sense. And so the use of empty literal construction isn't universal. And by the way, if I substitute T for a slice, that's not 0 value construction either. That's empty construction, empty literal construction. There's the semantic, isn't it? There it is. And so it's not giving us 0 value. This won't even compile. So we need a way of being able to construct a value of any type T to its 0 value state. Now there's only 2 ways to do that in the language today. I'm showing you the first way right here in line 59, and that's use of the keyword var. Var is a universal way of being able to construct a value of any type to its 0 value state. And if you take any of my classes, within almost the first half an hour, I am telling you to use var for 0 value construction, because it is the most consistent way to do that, whether this is a user, whether this is an int, or even if this is a slice. That gives you 0 value construction. And so this is saying, let's construct a variable named 0 of type T to its 0 value state, and then we can use the 0 variable for the return. Now, I like this in terms of the readability. We wouldn't do this if we weren't working with a generic type. I could just say 0, or I can just do the construction, but I like this. But there is another way to do 0 value construction in Go that would be universal. And it has to do with the built-in function new. New constructs a value of any type to its 0 value state. However, new uses pointer semantics. You get back the address. Therefore, for the syntax to be valid, we have to dereference the pointer. Now, I don't like this on many levels. First of all, I have a major rule that says you do not make copies of values that pointers point to. There's integrity issues there, regardless if there's going to be one here or not. It kind of violates a major integrity rule that I have. And so, 1, I don't even want to see that. But 2, how many Go developers are going to look at that code and instantly understand what's happening there? I don't think as many as we would like to pretend there will be. That syntax just isn't necessarily obvious. And so, for those 2 reasons, I'm not a fan of this, even though that would reduce a line of code. But I have a big design philosophy guideline that I follow for everything. It is a ground floor guideline and design philosophy. And it says, don't make things easy to do. You make things easy to understand, even if that means we've got to write a little bit of code. Now, I could argue that this is making things easy to do because we're doing the construction on one line. But is it easy to understand? I don't think so. So I'm going to go with this, at least for the code that I write, because I think it's just going to lend itself to better readability, more code comprehension, and that includes more developers without having to get through this whole educational process. Plus, dereferencing pointers is a big smell for me, and that's what we'll need to do. So there it is. We now can do zero value construction universally by using the keyword var and a variable, and I like that. Okay, let's see this code run a little bit. Now, Benjamin, you're right. We could move this here, and you could keep it closer to the return. And I've played with that, but I feel like now if you have multiple returns, you're going to end up with multiple variable declarations. And after some time, I said, you know what? Let's just do it once, and we'll just use it. But again, these are things that we're going to have to kind of decide as a community the best guidelines and idioms that we're going to want to follow. All right, let's run this code a little bit. So a larger main here, but look at here. I'm going to construct my vector int. This is the first type that I started with, right? And you can see I'm using literal construction to pre-populate it with a couple of integers there. But what's nice is that when I call last, I know I'm getting back an int. So I can apply logic like this. Hey, is it a negative number? Let's do some stuff. I know it's an int. So I can apply the right verb, %d. I can do some output. Same thing with a string. I can use my literal construction. I can apply some strings to the vector. When I call last, I know I have a string. I can do specific processing. I can use the right verb. Everything's good. But when I worked with my vector interface, remember I talked about that usability loss. Notice that when I'm doing a construction, the literal construction of the vector interface, I'm mixing data. Int, string, float. Which means when I call last, I get back that float in a decoupled state. I don't know what I got. All I know is I've got a concrete value decoupled behind the empty interface, and I don't know anything about it. So what are we back to doing? Either reflection or type assertions. If I have to do this type of logic, right? If I have to do that type of logic, or I got to use a %v because I got to ask the func package to now leverage reflection to do what it's got to do. So I think you have usability issues there. Now, here's the big win again, right? The big win here is I can construct a vector, and in this particular case, I'm telling the compiler it's going to be int. Now, hold on a second here so we can understand something. If I want to construct a vector to its zero value state, then there's nothing that the compiler has that will allow it to infer the type at compile time. So zero value construction will require that we explicitly tell the compiler what t is going to be. It's still determined later, but just not at compile time. It's going to be determined here at the construction site. However, like you're seeing here on line 110, I'm also specifying the type information. Why? Primarily for one reason. The current Go2Go tooling has not fully implemented every aspect of the draft document. In fact, we don't really want it to fully implement the entire draft document. That'd be a waste of time and engineering. We want to spend the bulk of the time actually implementing this in the compiler. So if I leave out the type information here, I'm going to get a compiler message not because it's bad syntax, but just because it hasn't been implemented yet. And we'll run into that on occasion with the go-to-go tooling. But when the compiler is fully implemented, this, using literal construction, the compiler now has information to infer what type T is at compile time. So these are our two construction syntaxes. This would be a zero value construction. This would be literal construction, and we wouldn't have to worry about passing it in. I'm passing it in because not the compiler, but the go-to-go tooling hasn't implemented the ability to infer this right now on this syntax. But you can see here that we can construct a vector with integers, which means last returns an int. We can do our negative processing. I can use the right verb again. We can construct it with strings. Last returns a string. We can check it. We can use the right verb. And so we're back again to our concrete implementations that can be generic, and we're back to our language syntax, our language mechanics. So we get, again, the higher levels of readability, higher levels of code comprehension, and those higher levels of maintainability. And as you know, what we're really trying to accomplish here again is, instead of having to write another vector that can work with a float 64, that we're able to do this, right? Boom. We're able to do this. Maybe we call this gen float. We come in here. We're going to have to declare a variable named f, but now we know that f is a float. I can do a negative float processing. I can use the correct verb because we're working with the actual concrete type that we declared here on the construction call on line 115. And sure enough, there it is. Our float is now in play. Beautiful, beautiful. Again, the whole point, though, is that we're able to write Lex code, use our language syntax, use our language mechanics. And this example comes with some interesting discussions that we're going to have to, as a community at some point, identify here as how we want to do our best practice. And the compiler could potentially, or the language could potentially, give us some extra support for this. Just not the highest priority right now. So this is what we have if you're going to experiment with it. All right. Now that's a type using underlying types. But you know, the majority of the types that you probably declare, that I declare, are struct types. So let's get a general sense of how we could use generics with a struct type. And for me, one of the nice ways of looking at this is by starting to implement a container type like a linked list. So let's implement the beginnings of a linked list. And once again, I'm going to take this out. And what you're going to see on line 16 is me defining a type named node. Now, a linked list is a collection of nodes that all point to each other. And the idea here is that I don't want to implement a linked list for just one type. I want to be able to implement this list one time where we can store a value of some type T to be determined later. What happens every time I say some type T? I have to apply the square bracket syntax to the, in this case, the type name again, because I want the compiler to recognize that T is a generic type. Look at the next and previous pointers, right? They have to point to a node. Again, it can't just be a node, because nodes in and of themselves, that's not enough information. It's a node of what type of data do we store. In this case, it's going to be a node of the same type T that we're using to construct this node that we're storing data for. You saw this syntax already with the receiver type. Same thing, same thing. So anytime we're going to have a generic type where we're going to be passing, whether we do it explicitly or not, generic type information, that type will be with the square brackets, a node of some type T. Now look, here's list. List has just two fields. It points to the first and last nodes in the list. But again, a node in and of itself is not enough. It's got to be a node of some type T. We don't know what type T is going to be yet during this declaration. So list is also a generic type. that can accept a type of any, right? T can be of some type T, and we've got our first and last nodes. Now, to make this example a little more interesting, I provide a method named add. Now, add is using pointer semantics, so it's binding to the list. There it is. That receiver, by the way, since this is a method, right? It's not a function. If this was a function, we would have to do this. But it's a method. And so this syntax isn't necessary here because we're already getting it through the type declaration. So we got our pointer receiver, a list of some type T, a method add that accepts a value of some type T, and this returns a node of some type T, a pointer to a node of some type T. Now here's the big win, right? Here's the big win. Look at the 11 lines of code I had to write for our add. If you look here, out of the 11 lines of code, 7 wouldn't change regardless of what type of data we need to store. In fact, if we probably looked at a full implementation of a linked list, I bet you, and I don't have the actual numbers, but I bet you 80, 85% or more of the code is exactly the same regardless of what type of data you're storing. This is what makes writing container types so horrific in Go today, because you have this high maintenance cost where there's just very little change depending on the data. Really, the only thing that's changing is the construction of a node, which now is constructed with some type T to be determined later. So we can assign data to data and a pointer of that node type to previous. There it is. This is the win right here. This is the win, right? This is what we're going for. So let's just see this run real quick. So I'm going to define a type named user. There it is. It has a name. And there it is. I'm going to do zero value construction of a list on line 55, zero value construction of a list. Because there's no way to infer the type at compile time, I'm going to explicitly tell the compiler that this list manages users, which means that the add method now accepts values of type user, and the data field is a value of type user. We're substituting T here explicitly on construction. Here, we're going to use our pointer semantics. We're going to construct a list set to its zero value, but this works with pointer semantics. Pointers of type user, add now accepts pointers of type user, data is pointers, which means that if I build and run this example, Fumpt is showing us values, Fumpt is showing us addresses. There it is. And if I define other sorts of types, I have one single list implementation to rule them all. Okay, it's 3:03. So there's 2 more examples I have to show you. And they come back to the ideas of constraint. And this is where things get a little bit more complex, and actually cases where we're also going to need some new syntax. But let's talk about constraint for a second. Up till now, everything I've done, like with those generic functions, have been, Eric, show me for a second. So everything that I've done so far has been code where it really doesn't matter what T is substituted for, what concrete type we actually use, because the code can be applied to all types. But that's really not a reality for a lot of the production code that we're going to write. There's going to be code we write where T just can't be anything. It's going to have to be constrained. Now, there's 2 areas of constraint here that I want to show you. One is behavioral constraint, where we've got to make sure that the data behaves in a certain way, like our traditional polymorphic functions do. And the other one is going to be what I'm going to call operator constraint, right? What operators can we apply to the data based on what we're doing? And I'm going to show you these last 2 examples. It's 5 minutes after the hour. It's probably going to take another 15 minutes. We're going to be about 5 minutes late here. But just giving you that heads up. These are really important because it gives us this kind of real big final piece of the draft here. So Eric, let's come back to the laptop here. Let's focus on some behavioral constraint. So on line 13, I go ahead and I define 2 user-defined types, two-struct types, a user and a customer. And for both of these types, I go ahead and on line 18 and 27, I add a method named string that returns a string. Now, the idea of this method is to provide intelligence on how to stringify a user or a customer. It really belongs here. Why would I ever want to stringify a user or a customer? There could be lots of reasons. Maybe you're logging this data and you want a very specific format in the logs that's readable or parsable, or, I mean, we can go on and on and on why you might want to stringify something, but here it is. This allows us to stringify these two users. Now, or I mean, these two entity types, a user and a customer. Now, to make this example a little more interesting, I wrote these functions here called stringify. What they do is they take a bulk or a collection of that entity type, a collection of users or a collection of customers, and all of those get stringified in one shot, and then the stringification is returned back in a new slice where the index positions match. So if you look at stringify users, right, we use the built-in function len to figure out how many users we have. We can construct the new slice of that right capacity. Then I use our traditional for range mechanics, language syntax and mechanics, to do the linear traversal. Then I use the built-in function append to accept the stringification of a user, which is done through the method string. The big thing here is that we need the method string to do the stringification. But the rest of these 5 lines of code, again, high levels of readability and code comprehension because we're using language syntax and mechanics. And if you notice, we're using 2 built-in functions, len and append. And if you want to just kind of think about it, len, append, make, copy, delete, and all the other ones I'm forgetting, close. You know, those are technically generic functions, aren't they? I mean, they're only capable of being written by the language team as part of the language itself. We can't write them, but aren't they generic functions? Does it append take a slice of any type and a value of the same type and perform that operation? Yeah. I mean, when you really think about it, between the reflect package and these built-in functions, there is a form of generics, but we can't use the language mechanics the language team uses for append, so that's kind of off the table. And we already talked about how the reflect package is an API-based mechanic, which doesn't lend itself to better readability. So I still think it's nice to have the generic syntax here. Either way, both of these functions, the same 5 lines of code, the only thing that's changing are the variable names because essentially the type is changing. And we have to make sure that we can call string, which we can. Compiler can check that. I'm not going to go through this. We already went through this exercise, but here's the consolidation using a polymorphic function and type assertions. You get it, right? In this case, there's a lot more code duplication anyway. Again, because of time, here is a generic version of stringify. Look, 13 beautiful lines of API code that I promise you, when I stare at, my head hurts, even though I wrote it. This code is not easily comprehensible, right? Like we know if you walk through it, it's potentially value of, so we can inspect. Is it a slice? No, get out. If it is, construct a new slice. But we can't use the built-in function len. I got to use the method len. Great, I can't use my for range mechanics. I can increment I over len. This is kind of cool. I got a truck coming by here, I'm sorry. I can do the following. I can ask at runtime through reflection, does the value at this index position have a method named string? If it doesn't, I'm out. If it does, I can call it. I don't know if you've ever knew that, but I can make method calls right there at the reflect package. It's not obvious, but there it is. And then I can finalize my append. So this is a full generic version of my stringify function using the reflect package API. Again, maybe we got the maintainability because it's all in 13 lines of code, but our reading comprehension, our code comprehension is gone. Okay. Now, once again, I'm going to pull out the generics piece so we can talk about it. And at this point, you already know what I'm going to say. I'm back to my same 5 lines of code that I wrote when I was writing my initial concrete versions of this function. You know I want to tell the compiler that stringify accepts a slice of some type t to be determined later. But since t will represent a concrete type, since this will represent a concrete function, I'm back to using the built-in functions. I'm back to my language syntax and mechanics. I'm back to my high level of readability and code comprehension and maintainability. But as you know, t is a generic type. So I would blindly just, out of the capitals here, I would blindly just do this. Now I'm going to build this code. Forget about main, okay? I can pass data to these functions. Not important right now. What's important is I'm going to build this code. We're in example 4. And I get a compiler message. I really want you to look at the compiler message here, because on line 114, the compiler is saying, Bill, we have a problem. You're calling a method named string for some type t, and there's nothing telling me that t, or a value of some type t, knows how to string. You're saying t can be anything, Bill. Guess what? No. So you better make it clear to me that t can be a type that knows, or a value of that type t that knows how to string. Now, let me do something here. Look, I can write concrete function like this. You know why I call this a concrete function? Because this function accepts data based on what it is, and it can only accept this one concrete piece of data, which is a user. However, I could write Bill like this. This is a polymorphic function. This function is no longer saying that I will only accept a user value. What this polymorphic function is saying is I will accept any piece of concrete data, any value or any pointer, as long as it implements the full method set of behavior defined by the stringer interface, which is one active behavior string that returns a string. This is polymorphic because it's asking for data not based on what it is, but based on what it can do. Remember what polymorphism actually means. It means that a piece of code changes its behavior depending upon the concrete data it is operating on. Line 16 changes its behavior depending on the concrete data it is operating on. You pass in a user, you're stringifying a user on line 116. You pass in a customer, you're stringifying a customer. That code changes at runtime. This is why I'm calling it runtime polymorphism, because at runtime, at some point, you pass in a concrete piece of data that exhibits that behavior, and then that behavior is executed. There it is. We can do that. But isn't this polymorphic function, isn't this interface defining a constraint against what the data can be? Of course. It's not saying the data can be anything. It's constrained to just that data that can exhibit the full method set of behavior. In other words, the concept of constraint against behavior already exists in the language through the use of the interface. The interface declares a method set of behavior, a constraint. And the compiler can check that to validate at compile time that the data you plan to run through that function at runtime will have that behavior set up in that I table behind the scenes. Great. And so what the draft says is, why reinvent the wheel? We already have interfaces that define behavioral constraint. And in this case, our problem is we need to constrain T to just be types whose values we'll be able to string. So the compiler says, if we're using interfaces today for our traditional runtime polymorphic functions, why not use the interface for our new compile time polymorphic functions? Why don't we now say, well, T can only be a type where the data of that type T exhibits the full method set of behavior defined by stringer. And that gives the compiler enough information at compile time now to validate that anywhere we make this function call to stringify, we can guarantee that a value of that type T is going to be able to string. And by doing that, the compiler message goes away. So there's nothing new going on here. Remember, we have our traditional polymorphic functions that happen at runtime where that function changes its behavior depending upon the concrete data we pass in. The interface defines the behavior. These generic functions are concrete functions, but they're also polymorphic because this code here changes its behavior depending upon the concrete data that we end up passing in. But we're doing it at compile time. We're setting it up at compile time. Okay, pretty cool. Now, very last thing. And this is new. This we don't have in the language yet. There's another form of constraint that we don't have with our traditional polymorphic functions, because our traditional polymorphic functions are all based on behavior, method sets. But we do have problems now with our generic functions because of operations. Let me show you. Let me hide a couple of things here, and let me get rid of the generic syntax. This is our last example. Look at this function. You know what I want to do here. I want to write a function named add that accepts a value of some type T and a second value of some type T, adds those two values of type T together, and returns a new value of type T. There it is. Now again, type T to be determined later. Okay, Bill, we know this already. We know the drill. There it is. T is now a generic type, but uh-oh. Can T be anything? Well, I don't know. Let's ask the question. Can T be an int? Yeah, I can add two ints together. Can T be a string? Yeah, can add that. Can T be a user? Nope. Not if it's struct type. Nope. Can't add that. We don't even have that concept in the language. And operator overloading is not coming anytime soon, so there's a problem. T can't just be anything. In fact, if this was a subtraction, it couldn't even be a string. Can't subtract strings. So T can't be anything. However, is this based on method behavior? No. So suddenly we need some new syntax because we have to be able to tell the compiler that T can't just be any concrete type, but only concrete types that we can use in this add operation. How are we going to do that? Let me show you what the draft syntax has currently settled on. Now, the decision right now is still to use an interface to apply constraint to the generic type. I kind of like that because I don't want a new type. I don't want a new thing. Interfaces define constraint. That's fair. However, this isn't behavioral constraint. It's more around a subset of types that conform to the operator. And so the current idea, and the one that seems to have stuck, is to leverage the interface and declare a type list of those types that T can be. And therefore, that will be the constraint. So T can now only be the subset of those scalar types. Now, what's nice is the scalar types cross packages. So if I defined a type named Bill, which had an underlying type of string, the underlying type matches that list. See, I don't have to do this. The string already matches. But if I use the Bill, it's kind of limited because that type Bill belongs to the package that's defining the interface, and you wouldn't be able to extend that interface for other types. So being able to match the underlying types can become important. The other problem here if we want to talk about potential problems with this syntax choice, is that you now have an interface that can't be used with traditional polymorphic functions. That doesn't even mean anything, right? Remember, on line 16, that function is supposed to say, I will accept any piece of concrete data, any value or pointer that knows how to add only. Well, add only don't know how to do anything. There's no behavior. So you're not going to be able to use the interface in traditional polymorphic functions. Once you define a type list, even if you do combine a type list and behavior, which I've not found a single practical reason to do so yet, by the way, though this is fine and legal, you're only now going to be able to use this interface as it relates to your generic functions. Now, again, I don't know if this is practical. I've not found a reason to combine type lists with behavior, but it's currently supported and something that you can experiment with. A couple other ideas here before I'm done is the idea of having some pre-declared type constraints like comparable, where you don't have to define this yourself. So if you use this type constraint, then it supports any logic that you're writing that requires the use of that double equals right there, right? Where you can compare it. So that's kind of nice. And there's ideas that maybe there are more pre-declared identifiers, or maybe we end up with a package in the standard library with a bunch of these common interfaces that apply type constraints to things that we're going to need. But we're going to have to see how that develops over the next year. There's some more interesting things in example 5. I'm not going to be able to get to it because of time. Eric, can you show me? But that does lend itself here to the bulk of what that draft document syntax is. And really the new syntax, one, declaring those type identifiers with the square brackets and constraint, and then that new kind of interface constraint for those generic types when we're dealing with operations more than method sets of behavior. Okay, so that's the talk here. I answered one or two things, I think, as I saw comments there. I didn't really go through the rest of them, just not to break up the flow. So from the organizer's point of view, we still have 20-something people here, so that's nice. One of the things I've been doing at the different meetups is just kind of walking through in the, not the speaker view, but the other view, the gallery view, and just walking through the names and asking if anybody had a question and or comment, understanding to keep your comments down to 1 to 2 minutes. That's what I've been doing. It's a larger group, so I don't know what you want to do as organizers here to give everybody that chance.
I think that we should just have people write a hand in the chat or something like that if they have something that they would like to comment on or ask about, and then we can just take them from there.
So, yeah, I just saw one comment come up from Anda. To speak to his question, so that means we write less code using generic constructs, but behind the scenes, the compiler will have to generate code. So here's the thing. We don't know what decision they're going to make in terms of generic code. I can simplify it down to 2 decisions. They could decide to write out each individual type, function, and method for each type substitution. Now, what's the advantage of that? The advantage of that is you would have real concrete functions that could potentially help with some reduction in escape, right? Could help with some reduction in escape analysis and in escaping and allocations to the heap. But what's the disadvantage of that? The disadvantage of that is larger binaries and longer compile times. And since we are a language that really values compile time, I think what will end up happening is they will use the same language mechanics they're using for the built-in functions, like append and make and there. And they're going to write one generic function and one generic everything and run it through there. And this is why I said, don't think about this from a performance gain, because I think you're going to end up having just one implementation of everything actually underneath, all right? Because that's going to give us the better compiler performance and the actual application performance. They've done so much work over the last 3 years with inlining and the new scheduler now and all these other crazy things that I don't think we need it there, all right? But now they're just starting to experiment with that. So we'll see which way that goes. But if I was a betting person, that's the direction I would go in. Thomas is asking, somebody's going to say something? All right. What do you think of the draft not allowing generic methods on type, only having functions with type parameters makes, well, I don't really like chaining functions anyway. That's not really a Go idiom. You see that in languages, at least I've seen them in Java and C#. And so I'm not a fan of that mechanic anyway. I don't remember the technical reasons that they made that kind of decision there. So I just don't have another answer for you there. I apologize. But I'll send you my email address when we're done, and you can send me that question again, and I'll get you a better answer. But I don't like that type of API style anyway. So for me, that's not a big loss. Do you know of planned extensions to standard derived from adding generics? I'm expecting that you will see changes to the standard library in a couple of places. I think the sync package related to map and pool is an excellent candidate to get rid of the empty interface there and to use generic types. I have in example 13 work that Roger Pepe did on looking at what the IO package could look like with generics, though I don't think it's necessary there because our runtime polymorphism works fine with that, but it shows you some areas there. So I think sync for sure. And I started to experiment a little bit with some concurrency patterns in the repo. I don't remember what number that is. It's number 10. So I think that we'll be able to see, it will require you passing in worker functions, but I think we'll be able to see finally the basic concurrency patterns like fan in, fan outs, pooling, all of those things you can imagine finally in the standard library. I think there's so many bugs today in software around these concurrency patterns since everybody's writing them themselves, that once we get those in the standard library, I think it's going to reduce a large amount of bugs, and I think it will clean up a lot of code. So at least those two for sure. And then, like I said, there may be a package of pre-declared interfaces for these types of constraints that we need. So from my perspective, at least there, okay, sync, new concurrency stuff, and maybe some pre-declared things like that. I don't see any other questions, at least in the chat. I saw some discussion on the zero value. Yeah, it's interesting. It's just a lower priority. So I don't know if they go back and do something to streamline that. They're kind of happy with the var and the other syntax. So I don't think they're going to do much there. So those are the only questions.
I have another question. So, with regards to the type lists in the interfaces, that seems a little bit odd to me. Like usually the interfaces describe the behavior of some type, and then you suddenly have a list of types in there, and you can't use the interface or like you'd usually use it. So that seems a bit odd to me.
They're not happy with it either. I had a discussion with the language team on that, and they were like, ugh. But no one's been able to come up with a better solution. Some people have suggested maybe instead of using an interface there, just putting the type list inside the square brackets or the operators in the square brackets, but there were technical reasons why that stuff wouldn't work. So No one has been able to find a better solution to that problem, at least right now. But you're not alone. If you talk to the language team working on this, they'll say, I agree. Let's find something better. We're all ears. All right. Does anybody have any other maybe comments or some thoughts they'd like to share? Just feel free to open up. If you can open up your mic and then it looks like we're good, huh?
I think so. If there's no one left that wants to ask about something.
One of the things that attracted me to Go was the simplicity. Do you feel the language will become too complex? No, I think that if this is used wisely, where it is going to help reduce the complexity that's already there through type assertions and reflection. And I love the reflection package. There's between marshalling and data validation, I don't want to get rid of it. Then I think it's going to help enhance readability and comprehension. Will people abuse this? Doesn't everybody abuse channels their first year they come into Go? So yeah, and everybody learns a year later and they rip it all out. And we've got 10 years of that knowledge. So I'm hoping that we take the last 10 years of channel abuse and we apply it to generics. And the fact that generics are not going to be the answer to performance problems is going to help. Because if suddenly it was told that, oh, if you write that in a generic function instead of a traditional polymorph function, will run by 10 nanoseconds, then everybody will jump to it. So I almost want to make sure that our generic functions aren't faster. So we still focus on what is the best mechanic for the readability, whether it's a traditional polymorphic function or not. But I think anywhere there's a use of an empty interface, especially on a return today, and the type assertions and the reflection are making things difficult, that's going to be a home run. Now, one other thing I've asked the language team, and I hope to be a part of it, and I wouldn't be the only one in the community that can be a part of it, is I've asked them if we can make sure that there's a lot of documentation, almost a clear set of guidelines on when to use this, when not to use it, a clear set of examples where it can be really valuable, maybe where it can't, and have all of that in place before that first actual release. That way, all of us who are teachers, whether we like it or not, in our shops, can leverage that documentation as a way of saying, whoa, a traditional polymorphic function is going to work here just fine. Let's use that. We're going to use generics when that doesn't, right? When that's not the answer, and our readability is way low, our maintainability is way low, then we can consider it. But we're going to have to do that as a community. So are there going to be some projects that are going to be now overly complex? Yeah. But I think this is a really important tool to have in the language. And here's the other thing, and maybe I'm being selfish here. I have a company that is a consulting training company. My company is built on growth in the language. And there are 1,000, if not more, enterprise companies on the planet who would use Go if there was a form of generics that would allow them to build the frameworks and the things they're building today, because they feel like without the generics, they've got to write and maintain too much code. We can debate whether that's true or not. That's not my point. My point is that if this language feature can be done in a way where it still looks and feels like Go, and can bring in another 1,000+ enterprise level companies into the language, that's 1,000 more companies that have jobs. There are 1,000 more companies looking for work, providing work. It's another 10 years of this language being out there. And to me, I want that. So I'm willing to be out here trying to educate when to use this, with the hope that we can grow the language beyond where it's currently being used. When we get generics, we will probably see a lot of people migrating. I'm hoping that we do now. I will tell you this first release of generics may not have enough, right? Like we're really focusing on the we're really focusing on the empty interface, type assertions, and reflection for the most part with this implementation. There's some cool things I didn't show you that I think can add some value as well, but it may not really be to another version of generics where we maybe cherry pick some of the things in the emissions list that the enterprise companies are saying. Now, I don't want meta programming, but let's just say those 1,000 companies say we need meta programming. Now a decision has to be made, right? And I'm not the one making it, and I'm not saying that we're just going to blindly say yes. Look, it's taken 10 years to get here. So I just don't know if this first release is enough to bring in how many of those companies just yet. I imagine that it's maybe not enough, and maybe we need another release or two. I don't know. But yes, Benjamin, for sure. I mean, that's the enterprise companies today are using C# and Java primarily for the big frameworks and systems they're building. So that's the idea. Okay. If nobody else has anything else, I really appreciate you all staying with me for this hour and a half. I know it's a late night. I hope that you feel like you have a better understanding of the draft proposal, the new syntax, what is there coming. Eric, can you drop those 3 links one more time, please? I'm going to drop the 3 links when we're getting, and then drop my email address, please. If you have any other questions or comments and things you want to send me an email, Eric's going to drop the email. It would be great if you can give the Go team some feedback. Definitely click on that Google survey. It's anonymous, so you can say whatever you want, good, bad, ugly, friendly, and let them hear from you. And yeah, hopefully again, I hope that you enjoyed the talk and now have a better understanding of what's being proposed for August next year, February 22.
Thank you very much. It was a very great talk. And before everybody leaves, we just have this short raffle. So now that's, I think, 7 or 8 people already left. So your chances for winning are getting a lot better now. So I'm going to share my screen, hopefully. Share screen. Find the wheel. I hope you can see the wheel now. And yes, awesome. That's a thumbs up. So the prize today is sponsored by TradeShift. It's an AeroPress, and I think there's some coffee beans coming on the side of that as well. So let's just do this. I don't think you'll get this sound, but let's see how it goes. We have a winner. Igor. Is Igor around? Is he here? Can somebody see? I can't see the chat right now.
He's not on the participant.
Igor's not here.
We will remove him and try again.
Oh, poor Igor. Oh, man.
Too bad. Too bad. Gotta stay around.
You always win when you're not around.
Lasse Højgaard.
Yep. They're here.
He's here.
He's here. Awesome. We have a winner. Congratulations, Lasse. And Benjamin will reach out to you to get some more details on how we can deliver the prize. I think, yeah, that was it for today. Yeah, thank you for staying around. It's been a really awesome talk. And again, thank you to Bill for doing this. I hope you learned a lot. I definitely learned a lot. So yeah, without further ado, I think we can give him a big round of applause, but do that anyway in the chat or something like that. And yeah, thank you for this time and hope to see you again another time. Do you want to say something at the end, Benjamin?
No, I think that covers it. Thank you for today, guys, and see you next time.
All right, turn it down.